We now move into our final unit, Unit 6. We're still in prescriptive analytics, and now we are moving away from linear programming just a little bit. We're going to go into integer programming. So, here are the LP assumptions that we had before for linear programming from the last unit. Objective function constraints must be linear. So we have proportionality, additivity, divisibility, and certainty. Now, this is highlighted in red because this is the assumption that we are relaxing or getting rid of. So now we're saying we have to have at least some variables as integer. So the other ones, proportionality, additivity, and certainty, still apply for integer programming. So when we actually require integers, what do we do? So suppose we solve a linear program and we get fractions, but fractions are not what we want, or we get decimals. Can we just round the fractional answers to integers and that will be okay to do? Will that be sufficient? Maybe, maybe not. So if you try to do this, and we'll see an example of this later, if you round the fractional answers to whole numbers, you need to make sure that you're still staying feasible. If you round the wrong way in one or more of the variables, you could quickly become infeasible, so something that would violate at least one of the constraints. So what we want to do is enforce the variables to be integers through our solver engine. Right? So that is going to be what we call integer programming. So integer program, sometimes called an integer linear program or an ILP. I tend to stick with IP or MIP for MIP, which is a mixed integer program. So in an integer program, at least some of the decision variables are required to be integers. May not have to be all, but at least some of them. If all of the decision variables must be integer, then we have a special case, which we call an all-integer linear program. If only some of the decision variables must be integer, then we have a mixed integer linear program, or MIP, mixed integer program. So I usually use IP or MIP when I talk about it. So the components of an LP, we have decision variables. So again, this comes from our last unit. The only differences are this bulleted item that's in red, right? So we have decision variables, and some of them now must be restricted to integers, right? The objective function, and still have constraints. So integer programming is theoretically much more difficult than linear programming. So what happens is we're going from a smooth surface in linear programming to a very point by point, much more discrete setting where if we have to have integers, we can't just get from one integer to another integer on that smooth trajectory, right? So we have to we can't traverse the outside of the feasible region like we did with the simplex method to find which corner point is the best. Here we have to enumerate sometimes a fair number of integer solutions before guaranteeing that we have found an optimal solution. Now, even though it is theoretically much more difficult than linear programming, it's still used regularly in real-world business problems. In some instances, if we solve just the LP, we do get integer solutions for free. So an example of that is when we have a totally unimodular matrix. So that's some linear algebra creeping in on you there. Don't get too hung up on it. We will look at an example towards the end of the unit that has this structure to it. And we'll show that if we relax the integer constraints to be linear, then we still get integers for free. That's a good thing. And then in practice, some IPs, integer programs, are not too difficult. A lot of it depends on their structure. So if it's a mixed integer program, is a lot of it linear, and then also is some of it have a nice structure to it that makes it easy to traverse from point to point.